So let's take a look at a couple of basic examples of using the power rule. So the power rule for derivatives, which tells me that to compute a derivative of a power of x, I should multiply by the exponent and then decrease the exponent by 1. And that if there are multiple terms, I can do that on a term-by-term basis. That's what the linearity theorem tells us. Let's apply that to compute some derivatives for some relatively straightforward functions that are in here. And the first comment that I have is that what a lot of people are going to screw up in a problem like this is they're going to look at functions like the ones in 3 and 5, and they're going to miss something. Namely, they're going to miss the fact that in both problem 3 and problem 5, as subparts of this problem, 2 squared and 12 times e to the 5th, those are both actually just numbers. 2 squared is equal to 4. 12 times e to the 5th is 12 times 2.718 dot, dot, dot to the 5th. So that's, each of those are just constants. And what did we say about the derivatives of constants already at this point? The derivative of a constant is always equal to 0. So don't be fooled by the fact that there's an exponent sitting up here in the 2 squared or in the e to the 5th, because the base is just a number. 2 is a number, e is a number. That makes these constant values, and so those derivatives are actually just equal to 0. So the interesting problems here are those in which we actually have a variable to think about. And let's take a look at them sort of one at a time. I'm going to jump around a little bit. Let's first take a look at part number 2. If f of x is equal to x to the 12th power, then how do I find the derivative of that? Well, according to the power rule for derivatives, there's 2 things that I should do. I should first multiply by the exponent, and the exponent is 12. So my first step is I'm going to multiply by 12. And then the second step is I want to decrease my exponent by 1. So instead of an exponent of 12, what I really want is an exponent of 12 minus 1. That's 11. And there we'll have a formula for the derivative of x to the 12th. It's 12 times x to the power 11. We can do that same process for part 4.
I've never seen somebody so lazy in my life. You know what they did?
Yeah.
They didn't even show us.
Sorry, if your
Can't talk.
if your microphone is on and you're not asking a question, would you mind just muting that microphone real quick? Because it's all going into the video. So how about 2x to the power 4? This is part 4 of this problem. According to the linearity theorem, if I'm multiplying a power by 2, I can take the derivative of just the power of x, x to the 4th, and this 2 is just going to come along for the ride. In other words, I can focus on taking the derivative of this x to the 4th, and then that 2 is just going to remain attached to my derivative the whole way through. So how would I take the derivative of x to the power 4? Same process. I want to multiply by that exponent. Sometimes people think about this as just kind of taking that exponent and bringing it out to the front. I'm going to multiply by the 4. And then I'm going to decrease the exponent by 1. So instead of x to the power 4, I'm going to have x to the power 4 minus 1, otherwise known as x to the power 3. So when I take the derivative of x to the 4th, what I end up with is 4x to the 3rd. But according to the linearity theorem, the derivative of 2x to the 4th, f prime of x, is going to be 2 times that amount. And so what I end up with here is not 4x to the 3rd, but 8x to the 3rd. And that'll be the derivative for the function here in part 4. F of x equals 2x to the 4th. F prime of x is 8 times x to the 3rd. And last but not least, looking at part number 1, if f of x is equal to 8x plus 20, again, because of the linearity theorem, I can focus here on each of the parts, each of the variable parts of this function. There's a secret 1 here in front of my 20. And what the linearity theorem says is if I know how to take the derivative of the function x, and I know how to take the derivative of the function 1, then I can piece together my derivative by piecing together the derivatives of those pieces in the same way. So starting with the function f of x equals 1, that's just a constant. And what happens when I take the derivative of a constant? it becomes 0 every single time. So that means that my derivative, if I'm building my derivative here, f prime of x, the second part is going to be 20 times 0. And of course, that in my answer is just going to go away. It's going to be a plus 0. Meanwhile, the x to the first power, which is in my first piece here, x to the first power, if I take its derivative, I'm going to follow again the same process that we did to take the derivatives of powers. I'm going to first multiply by that exponent. Let me clear out some space here. I'm going to multiply by the exponent, which is 1. And then I'm going to decrease the exponent on my x by 1. So the exponent is going to be 1 minus 1. Exponent is going to turn into 0. But what is x to the power 0? It's just equal to 1. So the derivative of x to the first power is just 1. And then according to my linearity theorem, I can piece that together by multiplying it by 8. And so all in all, the derivative of 8x plus 20 is going to be 8 times the derivative of x, which is just 1, plus 20 times the derivative of 1, which is just 0. And so my derivative is just equal to 8. Which again should make some sense given our notion that the derivative is the slope of a graph. And because this function, f of x equals 8x plus 20, is just a straight line to begin with, the derivative is going to be the slope of that straight line. And we know from algebra and from pre-calculus that the slope of the line, y equals 8x plus 20, is indeed equal to 8. So there's a bunch of examples of how to use the power rule in combination with the linearity, the linearity theorem for derivatives to compute the derivative of several types of polynomial functions. This one's 8x to the third, and this one is just 0. I'm going to pause the recording here in just a moment and ask if there are questions about this problem. Let me just leave these answers up on the screen for a couple seconds before I do. So let's push the envelope just a little bit more and look at how to compute derivatives for things that are actually power functions, but they don't sort of necessarily look like power functions when we first look at them. Let's start with this one here, f of x equals 6 over x to the power 11. How do we take the derivative of that thing, given that it's kind of got a lot of stuff going on? It's got like a fraction, and it's got a constant up in the numerator, and it's got a power of x down in the denominator. So how do we deal with that? Well, a little bit of algebra goes a long way. And I follow a mantra, and I recommend to students a mantra called ABC, algebra before calculus. So before we do any calculus steps, let's use algebra as much as we can to simplify the expressions that we're working with. So can we get 6 over x to the 11th to be a single power of x? And the answer is yeah, we can. We can do that just by taking the 11 powers of x from the denominator of this expression and just moving them up to the numerator, which comes at the cost of flipping the sign on the exponent. So 6 over x to the 11th is really the same thing as 6 times x to the power negative 11. So that little bit of algebra takes this from an expression that we don't know what to do with, calculus-wise, using the power rule, into something that we will know what to do with, 6x to the minus 11. Now that this looks like just a power of x, we can use the power rule for derivatives to compute its derivative. And again, because of linearity, we can just focus on the x to the minus 11 part, find its derivative using the power rule, and then the 6 is going to come along for the ride. F prime of x is equal to. And the derivative of x to the minus 11th is going to be, well, first we have to multiply by the exponent, and here the exponent is negative 11. So negative 11. And then decrease the exponent by 1. So we're going to have x to the power negative 11 minus 1, and this is a perfect place to make a sign error, so be careful when you do this. Negative 11 minus 1 is negative 12. And so the derivative of this function is going to be 6 times that. The 6 coming along for the ride, again, because of the linearity. And so the derivative is going to be negative 66 x to the negative 12. And I'm personally okay if you leave your answer in problems like this with a negative exponent. But for the practice, and in case web work might ask you to do this from time to time, we could take that x to the minus 12 and make its exponent positive again by bringing it down to the denominator. Negative 66 over x to the 12th. And then this problem in particular also asks you to do something with that derivative. It asks you what's the value of this derivative at x equals 1, what's the value at x equals 3. And for those, you would just evaluate this derivative function at those various x values. So that's one example of something that looks in the beginning like we might not be able to use the power rule for, but doing a little bit of algebra uncovers a way for us to use the power rule there. Let's look at one more that nips people a lot when they're taking derivatives. Let me go and find an example. I know there's one fairly close by. No. I think it's the last problem. Jump down to the bottom here. Yeah, here we go. So let's use this as an example. Let's suppose, and I kind of want to do two things with this. Let's suppose that we want to find the derivative of this function, first of all, y equals 6 over square root of x. And then the next thing I want to do with this is actually do the rest of this problem, because it's also asking us not just to find the derivative, but to find an equation for the tangent line to this graph at a certain point, at the point where x is equal to 1. So that's kind of a two-step process, and let's look at both of those steps. First of all, the derivative. I can't really find the derivative of this using the power rule until I use some algebra to rewrite this function as a power of x. For that, we have to remember actually two different things. The first is that the square root of something is the same, so this is a key algebra competency. Remember that the square root of a quantity is the same thing as that quantity raised to the 1/2 power. I taught an algebra course last semester, and I made a solemn promise to them that when we talked about this, it would be something that would come back to haunt them in their calculus class 2 semesters later. And so here it is. Rewriting the square root of something as something to the 1/2 power then is going to give us the link into using the power rule that we know in order to compute the derivative. But as in our last problem, we can't do that until we also take this power from the numerator to the denominator, sorry, vice versa, from the denominator to the numerator, so that we get that this is really 6x to the power -1/2. So we did actually 2 steps of algebra there to rewrite our original function. And now that our algebra has uncovered what power of x that we're dealing with, now we can use calculus, the power rule for derivatives, to find the derivative of this function. So f prime of x, because of linearity, the 6 is just going to come along for the ride. We can focus on the x to the -1/2. We need to multiply by the exponent, multiply by -1/2. And then we also need to decrease the exponent by 1. So we're going to have a -1/2 sitting out in front of the x, and the exponent is going to be -1/2 minus 1. Again, a perfect place to screw up a sign or to screw up a fraction subtraction operation. -1/2 minus 1, -3/2. And so the derivative is going to be 6 times that, again, because of the linearity property. And so at the end of the day, 6 times -1/2 x to the -3/2, that's going to give me -3 x to the -3/2, which again, I'm perfectly okay if you leave your answer in that form. But if WebWork or someone else wants you to rewrite it, we can also follow this algebra backwards, move the x to the 3/2 to the denominator, and then rewrite the fractional power, so that what we're really looking at is -3 divided by the square root of x cubed. That last step is, again, I would think of it as optional, but it's some good algebra practice, and there may be contexts in which you want to use it. So the important thing is, on the calculus side, how we actually compute this derivative. And it's, again, the same power rule that would be used for all the other problems. So we just went through the trouble of computing the derivative function for this function, y equals 6 over the square root of x. So the question here in WebWork, though, asks us to go one step further and also to figure out an equation for the tangent line to the graph of this function at a point that they've given us, 1, 6. So let's quickly take a look at what that would look like. I'm going to create a blank graph here in Desmos and graph y equals 6 over the square root of x. So that's what this graph looks like. And they're asking us for an equation for the tangent line. So let me do this, 6 over the square root of a. Give me a slider for a. So here's the point they're actually asking us about here, in my web work at least, 1, 6. We want to find an equation for the line that's tangent to that graph. Let me just draw in that line with Desmos here real quickly. This is going to be -3 times a to the -3 halves, x minus a plus 6 over the square root of a. Sorry for the typos. There we go. Zoom out on this a little bit. So this orange line here is the tangent line that we need to find an equation for. And we know really two things about this tangent line. We know that its slope is going to be given by the derivative of my function. So the derivative that we found in the previous example. We also know that this line is going to pass through the point 1, 6. Right? It's the point that was given to us in the problem. It's the point that's on this graph. So to find an equation for this tangent line, we really just need to do two things. We need to find out what is its slope and what is a point that it goes through. And if we find those two things, we can use the point slope template, which let me record that here at the top of the screen. Probably the most useful form of finding an equation for the sake of doing calculus. Point slope template is y equals m times quantity x minus x0 plus y0. So this is something you got a little bit of practice with in the first set of homework problems. X0, Y0 is the point that this line goes through. M, as usual, is the slope. So if we find those two pieces of information, then we can just plug those into the template. So the slope of this tangent line.
Sophie.
And again, if you're watching on Zoom and you don't have your microphone muted, please do, because this is going into the video here. So the slope of the tangent line is going to be equal to the derivative. Those two things should be synonymous in your head at all times. Derivative is the same thing as slope of a tangent line. And we found out a formula for the derivative in our previous work. That was -3 times x to the -3 halves, right? And because we're specifically looking here at the point where x is equal to 1, what I want is to evaluate that derivative at x equals 1. So I'll plug a 1 here into my derivative for x, and then compute. 1 to the -3 halves is, well, 1 to any power is equal to 1. Multiply that by -3. That's going to give me -3. And so what we find out is that this tangent line should have a slope of -3. So I'm going to put that into my point slope template up here. And then secondly, we actually already know the coordinates of a point that my tangent line needs to go through. Namely, x0 is equal to 1, y0 is equal to 6. So I can just plug in a 1 for my x0 and a 6 for my y0. And when I've done that, my point slope template has now given me an equation for this line. And for most purposes, you can leave this equation as it is, unsimplified. It's completely correct and usable as it is. If you would like the reassurance of getting this to be a slope-intercept equation, then all we really need to do is simplify out the arithmetic on the right-hand side. Distribute the -3 into the x minus 1. That's going to give me -3x plus 3. And then simplify the like terms, plus 3 plus 6. That's going to give me -3x plus 9. So if you prefer the slope-intercept formulation for this tangent line, you can use that version. But either one is totally fine, and it's my opinion that the point slope template really is the easiest one to use in problems that ask you to find an equation for a tangent line. Again, remember the two steps in finding an equation for a tangent line. First of all, find the slope. And the slope of a tangent line is always the same thing as the derivative. So when you have the derivative, evaluate the derivative at the point you're interested in. That was, in this example, x equals 1. And then use that slope and the point that you know that your line has to go through in the point slope template to get an equation for that tangent line.